Welcome back, and in this video we're going to be looking at catalysts. We know that catalysts speed up the rate of a reaction, so they'll always be involved in the rate equation even if they're not involved in the balanced stoichiometric equation. So you're going to need your notes, and we're on page 11. So a catalyst is defined as a substance which increases the rate of reaction. It does this by providing an alternative mechanism with a lower activation energy. And that's the definition of a catalyst, species which provides this alternative mechanism with the lower activation energy. Now we can divide our catalysts up into three different types. The first of these types is homogeneous catalysts. Now, homogeneous means they are in the same physical state as the reactants, usually as a solution. They quite often work by changing oxidation numbers. So here, for example, we have the reaction between iodide and peroxydisulfate ions, which you've studied previously in the iodine clock reaction. Now I can make this reaction much faster by adding a catalyst. In this case, I'm adding iron 2, which is oxidized to iron 3, and then reduced back to iron 2. So transition metals are very good at this because they have variable oxidation states, and it's quite easy to change their oxidation states. The second type of catalysts we come across are heterogeneous, and these, because they are heterogeneous, they are in different physical states or different phases from the reagents. Now, if you have a choice, you would always use a heterogeneous catalyst over a homogeneous catalyst. The reason for this is that they're much easier to separate than the homogeneous, because once you've got everything into one solution, it's quite difficult to separate it out again. So industrially, most often heterogeneous catalysts are used. And these heterogeneous catalysts work in three stages. Stage 1 we call adsorption. Now do be careful of the spelling of this word. You need the D in there. This is different from absorption. Adsorption is a surface reaction. So our chemicals or our reagents are adsorbed onto the surface of the catalyst. Absorption is a bit like a sponge. They would go internal, but these are surface-only reactions. So our reagents are absorbed onto the surface of the catalyst. Next, there's some sort of reaction. By bonding to the surface of the catalyst, that's weakening the bonds between the reagents, and it's also ensuring that reagents are held in the correct orientation. So it brings them more into contact. Lastly, we have desorption, where the products are desorbed from the surface of the catalyst. Desorbed from the surface. In other words, they become loose and release more what we call active sites, so we can adsorb more reactants onto the surface. So it always works via these three steps. Adsorption onto the surface. By doing that, that weakens the bonds and holds the molecules in the correct orientation so that the reaction can occur more easily, and then they are desorbed from the surface. So that's desorption. So you can see here in this little diagram, so I have my catalyst bed here, my solid catalyst, I have ethene and I have my hydrogen, and those are adsorbed onto the surface of the metal. This weakens the bonds, causing the hydrogens to become atoms. Those atoms then can bond, can react with the ethene, and then last step, that the product is then desorbed from the surface of the catalyst. The last type of catalyst you need to be aware of is enzymes. These are biological catalysts, and these are usually very specific. So they will only catalyze one particular pathway. Hopefully we've been able to do the experiments on page 12, so we're moving on to page 13 and we're looking at a reaction profile to show the effect of a catalysis or catalyzed reaction. So here in red we have the uncatalyzed reaction. You can see the activation energy for this reaction is quite high. For the catalyzed reaction, it happens via a two-step because it happens via a different mechanism. So there's a reaction to form an intermediate, and then that intermediate reacts to form the products. But the key thing to notice is the fact that the activation energy for this catalyzed reaction is much less than the uncatalyzed reaction. So if we do the same thing but for an endothermic catalyzed reaction, we have our reactants and our products, and our uncatalyzed activation energy is very high, so this is our EA for our uncatalyzed, but for our catalyzed it's much less. So you're going to get a much faster rate of reaction because I can go via this alternate mechanism with this lower activation energy. So lastly, we can show this on a Maxwell-Boltzmann diagram and the effect of a catalyst. So here is a normal Maxwell-Boltzmann curve with my activation energy. What a catalyst will do will provide an alternative mechanism with a lower activation energy. So all you're basically doing is moving the goalposts. So we did have to get this amount of energy and above to get the reaction to work, but I've lowered it. So now I have my catalyzed reaction, and these particles also have enough energy to react. So I've got a larger shaded area, so there are more particles that are able to react. So we have more particles with an energy greater than or equal to the activation energy. Now this is shown by the increase in the shaded area, the increase to the curve or the area under the curve to the right of the EA, so this bigger area here. Therefore you've got more successful collisions again per unit time and therefore a faster rate of reaction. Do notice that a catalyst will speed up the rate of the reaction, but it will not change the position of equilibria. So you'll just get where you're going faster, it won't change the ultimate destination. So catalysts will speed up the rate of a reaction by decreasing the activation energy, and it'll do that for both the forwards and the reverse reactions. So you'll reach the position of equilibria faster, but you won't change the position of equilibria.